In this lecture, we're going to take a look at difference equations. These can come in different forms, but we're interested in first-order difference equations that can be written in the form y sub n plus 1 equals some right-hand side, which depends on y sub n and may depend on n, and we'll call that right-hand side f of n comma y sub n. N here is going to index through non-negative integers. So typically we have a first value that we'll call y sub 0. And then using this recurrence relationship, we'll compute y sub 1. And then using that, we can compute y sub 2, etc. Okay, let's look at these three examples. I tried to throw in a little bit of different notation in number 2, but the idea is that's also a difference equation, even if I'm using a different notation. Okay, so the first one is y sub n plus 1 minus 4 sub yn equals 0. This is not written in the form up above, but let's convert it into that form. So I'm going to solve for y sub n plus 1. We can say that y sub n plus 1 equals 4 times yn. Now written in this way, our function is f of n comma y sub n equals 4 times y sub n. And is often the case for us, this function has no dependence on that first input n. It's really just a function of the previous term y sub n. So that can happen, and that's totally fine. Okay, let's suppose our initial seed is y0 equals 1. Then y1 is 4 times y0, which would be 4. y2 is 4 times y1, which is 16. So here we can spot a nice pattern. We're going up in multiples of 4. So if we write this out like a sequence, it would be the sequence 1, 4, 16, 64, 256, etc. In the second one, I've switched from the letter y to p, but that's not a problem. Here, p might refer specifically to a population or some principal amount in a bank or something like that. So first, let me identify the right-hand side. Once again, this has no dependence on the first input n. So I think I'll leave that off this time. I'll just write that the right-hand side is f of y sub n is 3 times pn times the quantity 1 minus pn divided by 100 plus pn. Suppose our initial seed is p naught equals 50. Now I could plug this in. I would get 150 times 1 minus 50 over 100, so that's going to be times a half, plus 50, I think that's 125. But let me show you a Matlab script that you can use to generate these sequence terms without too much computational difficulty. Okay, so here's a script I've written. Let's go through it. The first line just wipes everything out, so you're starting with a blank slate each time. The second line is an anonymous function of n and just plain old y. That's just denoting the second input for the function. And then you type out over here what that right-hand side is going to look like. So if it has n dependence, you would use the letter n, and then anywhere you would have y sub n on paper, you'll just type y. So for us, it's going to be 3 times y times 1 minus y divided by 100 plus y. And then on the third line, you put your initial seed, so 50. And then the rest of it you don't need to change unless you want to generate more terms than, say, through y sub 5. Okay, so I can run this code now. What we're going to get is a matrix. And what the matrix is going to do is in the left-hand column, it's the subscript n. So starting with 0 corresponds to 50. And then n equals 1 was 125. So I got that right with my little mental math, never quite sure. So that's why I like MATLAB so much. N equals 2, it's 31.25. N equals 3, it's 95.7, etc. If you wanted to generate the first 50 terms, you could do that. You would just adjust line 5. And actually, because it ends with the I plus 1th term, that goes all the way through 51. So you could do that. You shouldn't try to generate like a billion terms. That's just not a wise thing to do in MATLAB, but certainly if you want to look at what a sequence would start to look like, you could do this in MATLAB. So you can see this sequence is kind of bouncing around. In fact, we could even plot it. So how about we scatter the first column of M, so all rows first column, and the second column of M. Oh, I just realized I displayed the transpose of the matrix. Let me just adjust this code. I'll make it a little bit different. Okay, that's what we wanted to see. So now you can see the jumping around here. If you want to, instead of scattering it, you could plot it. And this is going to connect the points in sequential order. So how about we make it K and we'll do a square everywhere there's a point, and then it'll connect the points with a straight line. And let's make it a little bit thicker than the default. Okay, so there you can see how the sequence jumps around. Let me do just through 25, actually through 26. Okay, so you can see we started at 50 and then we kind of jump around like this. Our third equation, I just wanted to give you an example of when the right-hand side might depend on n. So here you can see that there are terms that just depend on n, and then there's also y sub n. So in this case, f of n comma y sub n would be -1 to the n times y sub n plus 2 to the n. Let's suppose the initial term in our sequence is 10, and let's see what this is going to look like in MATLAB. All right, so I've opened up MATLAB. Now I'm just going to change the second line. So I'm going to do -1 to the n times y plus 2 to the n. And then our initial seed is 10. I don't need any array operations here, but if you're trying to do something like this and it's not working, you can always try dropping some periods in there. Shouldn't be necessary here. If I run this, okay, once again, we get a sequence that does something funny out here. Look at the scale. So let me just go through, say, the first 10 terms. I just made this function up, so I'm not trying to hone in on any interesting behavior. Okay, so it looks like that, and then it starts to grow about just the first 5 terms, or really the first 6 terms. Okay, you can see we started with 10, then we went up to 11, then down to -9, etc. Now to analyze these difference equations, you can't just start plugging in like we were doing, but it's nice if you can find what's called a solution to the difference equation. So this is a function y of t, where if you plug in integer values of t, then it makes the equation true. So if you plug in 1 to your function y of t, you get back y sub 1. If you plug in 2, you get back y sub 2, etc. So given a sequence that we generate with a difference equation, can we find a solution? Let's look at an example where we can. Okay, this is a difference equation that we looked at when we first did those 3 examples. This time we're not going to have an initial seed, so we're going to solve in a little bit more generality. So let me suppose that y sub 0 equals c. Then y sub 1 would be 4c. Y sub 2 would be 4 times y1, which is 16c, or actually let me write 4 squared c. Y sub 3 would be 4 times y2, which is going to be 4 cubed times c. Okay, from this we can deduce the general pattern y sub n would be 4 to the n times c, where c is whatever our initial value is. We want a function so that y of n is 4 to the n times c, and now we can see how to do it. Okay, so I'm going to write this a little bit differently than I've written it the line above. I'm just going to switch the order of the terms on the right-hand side because I like it better. So we have y of t equals c times 4 to the t. And you can see that that would be true in general if I wrote down y sub n plus 1 equals r times y sub n. then the solution is going to be y of t equals c times r to the t. So there, t is our independent variable, y depends on t, c is like a parameter that's determined by our initial population or initial quantity, and then r is some kind of rate. Okay, let's apply what we've just done to this problem here. An initial amount of $1,000 is deposited into a bank that yields 2% interest compounded just once a year. Describe this with a difference equation, then determine the amount in year 20. Okay, so our initial value is p sub 0 is 1,000. And then next year we're going to have p sub 1 is what we had last year plus 2% interest. So that's going to be p sub 1 equals p sub 0 plus 0.02 times p sub 0. And then we can add like terms on the right and say this is 1.02 times p sub 0. Okay, and then p sub 2 is going to be p sub 1. That's the amount that we had before, plus 2% of that. So p sub 2 is p sub 1 plus 0.02 p sub 1. So just like the line above, that's 1.02 times p sub 1. The difference equation that models this is p sub n plus 1 equals 1.02 times p sub n. That means the general solution is going to be p of t equals 1,000 times 1.02 to the t. Now this is advantageous to the difference equation form if we're interested in year 20, because to get to year 20 using the recursion is going to be slow, because next I would need to do P3, then P4, then P5. We would have to get there step by step. But now I can just say, in year 20, we will have P of 20. And if you're wondering if this account has made us into millionaires, it hasn't. That's about $1,485.95. So in 20 years, we've gained a little bit less than $500. Okay, now let's take the form of the equation that we were just looking at and add a constant to it. So we have y sub n plus 1 equals a times y sub n plus b. Let's find the general solution to this and then we'll apply it to a problem. Okay, y0 is just whatever it is. Let me call it a constant. Y sub 1 would be a times that constant plus b. Y2 is going to be a times y1 plus b. So let me write that first. Now if I plug in the form above, that's going to be a times ac plus b, and then all plus b. So overall we get a squared c plus ab plus b. I think it's a little too soon to try to spot a pattern at this point, so let's do y sub 3. That's a times y sub 2 plus b. So then that's going to be a times the line above plus b. So when we expand that, we get a cubed times c plus a squared times b plus ab plus b. Take a second to try to conjecture what the next one will look like fully expanded, and then I will do it. Okay, let's see if you've spotted the pattern. So what is y sub 4? That's going to be a times y sub 3 plus b. But then that's going to be a times the line above plus b. Let's do that and then expand it. So then we get a to the 4th times c plus a cubed times b plus a squared times b plus ab plus b. Okay, I think now we can say what the general form would look like. So what is y sub n? Well, the first term is going to be a to the n times c. And then we get a to the n minus 1 times b, and terms that continue in that form where the power on a decreases all the way down to 0. So let me write a to the n minus 1 times b plus a to the n minus 2 times b plus all the way down to ab plus b. For everything but the first term, let's factor the b out front, and then we can write those powers of a in series form since we're adding up a sum. So this is going to be a to the n times c plus b times the sum. Let's see, we start with n minus 1, and then we're going to end with n minus n. So let me do from I equals 1 to n, a to the n minus I, terms that look like that. So let's see, if I plug in 1, for I get n minus 1, that's our first power, then n minus 2, and then all the way through n minus 1, and then n minus n. Okay, that looks right. This sum you should recognize as a finite geometric series. I find I always know the sum of the infinite geometric series a little faster than the finite one, but let me tell you what that's going to be. So we'll have a to the n times c plus b times, there's a simpler way to write this geometric series, give it kind of a closed form expression, and that's 1 minus a to the n divided by 1 minus a. So we can replace that expansion, that series expansion on the line above, with this nice rational expression. Okay, so now our solution is going to be y of t equals c times a to the t plus b times the quantity 1 minus a to the t all over 1 minus a. Now, if you look at the solution, you realize you have a denominator of 1 minus a, which means that this is only a correct thing to do if a is not equal to 1. What would it be if a were 1? If you look back here at these sums we wrote down, if a is 1, then the leading term is c, and then we have b plus itself 4 times. So if a equals 1 is actually quite a simple form. You would have y of t equals 1 times c, so c plus tb. Okay, whenever we recognize that we have a difference equation of this form, now we can jump immediately to the solution. So let's look at an example. All right, an annuity is a type of account that grows with interest, like the example we already saw, but also gets a regular deposit whenever the interest is compounded. So suppose an annuity account is opened with an initial deposit of $4,000. The account has an interest rate of 6% compounded monthly, and then each month it just gets a deposit of $200. So how much money is in the account after 10 years? The first thing we have to do is set this up as a difference equation so that we can put it in the form we were just looking at. That leads us to the general expression that we have at the bottom. All right, our seed is that initial deposit of $4,000. Okay, then nothing happens for a while, nothing happens, and then 1 month has gone by, at which point we're going to keep the $4,000 we have, we're going to add a 0.5% interest to that, and then we're also going to add $200 to our account. So we can write P1 is the 4,000 that we already had, let me just call that P naught, plus 0.005 times what we just had, plus 200. So that's what we already had, what we gain in interest, and then the deposit. Okay, let's write down what happens in the second month. So that's going to be P sub 2. Now 2 months have gone by, and what we're going to see in our account is what we had before. So that's P1 plus, we're going to add 5% of P1, and then we're also just going to add $200. Okay, we could continue in this way, and what we realize is that we have a pattern here of the form P sub n plus 1. In the n plus 1th month, we're going to have what we had before, so that's P sub n, plus the interest that we gained from that previous amount, so that's 0.005 times P sub n, plus $200. I kept those first terms separate so that it was clear what was being carried over from the previous month versus what we were getting from interest. But now that we have this general form, let's just put them together. So we can say that's 1.005 P sub n plus 200. Now that's the form that we were just looking at, where that 1.005 is what we were calling A, and then the flat 200 is what we were calling B. So the general solution is going to have the form at the bottom. So we'll say y of t equals c, that's 4,000, times 1.005 to the t, plus 200 times 1 minus 1.005 to the t over 1 minus 1.005. Okay, so how much money is in the account after 10 years? You have to be careful here. We're doing monthly calculations, so that's 120 months. So we can solve for that by doing P of 120, and that's approximately $40,053.46. So actually that went up pretty far from $4,000. Let's finish today with a game. So this is called the Tower of Hanoi. You may have seen it before. And the configuration is you have 3 pegs, you have a stack of discs in decreasing size, and you need to relocate this stack to the 3rd peg. You move 1 disc at a time, and whenever you set a disc on top of another one, the smaller one has to be on top, so you can't put a bigger disc on top of a smaller disc. Let me show you a website where you can simulate this. Okay, given any game like that, I have to play it to understand it. So here's the Tower of Hanoi, and in this case we have 3 discs, so large, medium, and small. I would like to take this stack and put it over on the 3rd peg. So what I'm going to do is first try to figure out how to get the big disc all the way over, because everything has to stack on top of that. So let's move the small one to the right, the middle one to the middle, stack the small one back on the middle, and then we can move the big one over, the little one back to the left, the medium size can go over, and now the small one. Okay, so it's pretty easy with 3 discs. It's not too bad with 4 discs either, so let me go up in size just one more time. Okay, now we have 4 discs stacked on top of each other, so the first move has to be correct. I think it should go to the right, and then I'll stack like this. Nope, I should have put it in the middle. Okay, because if I move that over, then I can't move this anywhere. So let's restart, and I'll put the little one in the middle this time, and then move the second to smallest one, and then like that. Now I've got to move these back to the middle, so I have to put the little one over on the left, and then medium and the medium, like that. And now I can move the big disc. And now you can see we're actually reduced back down to the first demonstration I did. We're just trying to get these 3 over to the right, from the middle to the right versus from the left to the right. So it's basically going to be the same algorithm. So let's put this one here, that one there, and I can move this here, that there, little one in the middle, and now we stack on the right. Okay, the first one was done in 7 moves. This one was done in 15 moves. So the question is, what's the best number of moves you can do for a certain number of discs? If we go up to 5 discs, I'm not going to try to do this one because I'll probably make a mistake. So let me just click the solve button. Oh, it tells you down here, minimum moves is 31. Okay, so spoiler, it's going to be 31 moves. Watching this, you can see that there's basically one train of thought. So there's always something you're trying to do. And then you end up with these kind of similar configurations. Okay, so that's the most efficient way to get those 5 discs from the left to the right. You can't do it with fewer than 31 moves if you have 5 discs. Okay, now that we've seen how it works, and also we know that there's some optimal number of moves based on, say, the number of discs, let's figure out a formula for it. So if we have n discs, how many moves do we need? Okay, I think this is pretty neat. So let y sub n denote the number of moves required. This is the optimal number to move in disk correctly. Given that, let's figure out what y sub n plus 1 will be, and it's going to be in terms of y sub n. So I can't tell you what y sub 30 is off the top of my head, but I can tell you what y sub 31 would have to be relative to y sub 30. Okay, so here's the principle. If I could move this stack to the third peg, I could move it to the second peg instead, using the same moves, just switching the role of the second and third pegs. So take the first in disk and relocate them to the second peg. If you need that first peg, you can use it because the disk that we're ignoring is the biggest one, and that can stay there no problem because you can move anything you want to on top of it. So we can almost treat this as non-existent until we actually move it for the first time. Okay, so y sub n plus 1, our first thing we're going to do is y sub n moves to relocate all but the largest disk to the middle peg. Okay, so at that point, where we are is we have everything except for the biggest one here. So I've taken all but the biggest and put it there. Our next move would be to take the biggest one down here at the bottom and just go ahead and move it where it needs to be. Let's move it over to that third peg. Okay, at this point we have the largest disk where it needs to be. We have all but the largest stacked on top of themselves on the second peg. And now I know that in y sub n total moves, I can relocate them. So this time, switching the role of the second and third pegs or whatever, basically we're going to take this middle peg configuration and place it on the third peg. And at that point, we're done. So we essentially break this problem into two components, moving all but the largest, then moving the largest, and then moving all but the largest again. But now we have an equation of the form we've been looking at, so I can write this as y sub n plus 1 equals 2yn plus 1. So I've put down here the solution of the general form of this type of equation. We have a and b. We need to think about c. Notice that if you had 0 disks, you would need to make 0 moves. So actually, y sub 0 is 0. So now our general solution is going to be y of t is 0, 2 to the t, plus 1 times 1 minus 2 to the t, all over 1 minus 2. This is going to simplify a lot. So we have 0, and then that's a denominator of negative 1. So let me write this as 2 to the t minus 1. Okay, so let's see if this actually makes sense. So is this a reasonable solution to this problem? Let's see, y of 0 is 2 to the 0 minus 1, that's 0. Y of 1 would be like, can I move one disk? You just need one move for that. So that's 2 to the 1 minus 1 is 1. For 2 disks, you need 3 moves. So that's 2 to the 2 minus 1. Yep, this looks good. Okay, so I hope you enjoyed revisiting the Tower of Hanoi problem if you've seen it before in terms of difference equations.